Hello, can you hear me? Perfect. All right. So very few people today. Hope some more people will come along. Maybe just a quick reminder for them. General. Yeah, 13 webinars started. Okay, and I'll just put that. What's the participants? Copy invite link. Hopefully we'll get some more people. But anyways, I'm recording this. I believe so. Yes, it is recording. So sorry for being late with the fourth assignment. So the fourth physics assignment will come out, and the fifth assignment will come out very soon as well. Okay, so you have two assignments, which you will have until. Well, you have assignment 4 was due 15th of January, so it's still a month to go. And the fifth assignment is going to be due 29th, I think, of January. So you have slightly more time. Assignment 5 will be based on A-level problems. Well, A-level, some pre-Q stuff. Today, I want to talk to you about assignment 4, physics, and this is waves. Yeah, so today we're talking about waves. And let me share the screen. And right, so this is how the assignment looks like. So make sure this is not the final version. There will be slight changes, not dramatic. But yes, you can start doing the problems. Most of the problems will stay as they are. Okay, so we are unlikely to see big changes in problems. There will be some changes in the theory bits. I'm working on it, but you can already start doing the problems. And the first thing is the wave equation. Now, in school, you might have been taught that the wave equation is this: V equals frequency times lambda. Well, it is an equation, it is related to waves, but the true wave equation is this. It's a differential equation of the second order. Okay. And this equation describes a wave propagating at velocity v. So x, it is important to understand what everything means here. So v is the speed of the wave, speed. X is the position in space, position in space. It's the x coordinate. Yeah, simply put, is the x coordinate. T is time, of course. And F is the displacement caused by the wave. Displacement caused by the wave. Okay, so just to put it simple, bed waves on a string. So this is a wave. Okay, so as you can see, this is a wave. You can see that the points are moving up and down, but the peak of the wave is traveling to the right. It is important to note that the points themselves do not move horizontally. Look at the green dot. The green dot just simply moves up and down. Okay, so the rope stays where it is. It's just the wave that is traveling along. All right, going back to this, just to make sense of this. How is it related? It's quite simple. So this is the x-axis. This is the x-axis. This is 0 on the x-axis. Oh, it doesn't have to be, but yeah, it's this. F is the displacement. So for example, here, for this point, F is 1 centimeter. For here, F is minus 1/2, minus 0.5, roughly, just for you to understand what we're talking about. V is the speed at which the wave propagates. T is the time. Okay. Is everything making sense so far? I mean, without looking at the equation is not easy, but does it make sense? Ooh, I got a thumbs up. Okay. Now, the wave function. So if this is the wave equation, the solution to the wave equation is the wave function. Let's say the wave function is a function of two variables, f of x and t, right? So for example, it could be sine, it could be 2 multiplied by sine k, well, 2x plus 3 or minus 3t, for example. It's 3t. Yeah, the white. Oh, you don't have the whiteboard link. It's the same whiteboard link as it's the same every time. Now, what does it mean? Like, let's look at this. Let's look at this wave function and try to make sense of it. Right. So let's take, for example, the point with x equals 0. X equals 0 is this point. So it's the green dot. X equals 0. Then f of 0t, yeah, because I've substituted 0 instead of x, is 2 sine minus 3t. Basically, it just tells us how the green dot moves, and that's it. So this is the equation of the green dot at x equals 0, and it's oscillating. It's an oscillating. It's an we can say that omega is 3 here, obviously. Yes, omega is 3, and yeah, we can take the minus out. Amplitude is 2. Amplitude is 2. And yeah. How much sense does this make? So this is a wave function. I put x equals 0, and it gives me the equation of the point the green dot at x equals with coordinate x equals 0. Does this make sense? On a scale of 0 to 10, please. Very good. Now, if I take x equals, I don't know, 2, we find a point where x equals 2, and it gives us the equation of this point, of this red dot at x equals 2. So f of 2, 2, 0, 2, sorry, 2, 2, 2t equals 2 sine 4 minus 3t. 4 minus 3t. It's the same. It's another oscillation. It's just with a different phase. So 4 is the phase difference. 4 is the phase difference. Phase difference. Okay. 4 is the phase difference. So it's lags, or simply, or lag. Because this red dot will lag behind the green dot. Because the green dot is the first one to start oscillating, and then the red dot catches up. Just like that. And another thing that we can do is we can substitute t. For example, substitute t equals 0. T equals 0. T equals 0. You have f of x 0 is 2 sine 2x minus 0. And this is the equation of the shape. That's the shape of the rope. The rope at t equals 0. It's the equation of the shape, because if you draw it as x, and it becomes this. It's just a snapshot. So this is a snapshot of the wave. Snapshot. At t equals 0. It's quite cool. I don't know if you find it cool, but I definitely find it cool. Right, so back to the differential equation. So let's try to work it out. So consider the wave function. So in the assignment, I will ask you to consider this function. Today, we're going to look at a somewhat similar function instead. Consider the function. By direct substitution, show that the function is a solution of the equation. So d squared f d is it dx squared? Dx squared. Yes, 1 over equals 1 over v squared d squared f dt squared. So first, you need to prove that this function is a solution of this equation. So we just plug it in. So we find df dx first. Now this is a chain rule. Can somebody help me with this one? Df dx is the derivative of f with respect to x. Two sine, it's going to be 2 sine x minus vt cos x minus vt. There's one thing I haven't taken into account. You know what? Can we make it slightly simpler? It's just the differentiation is going to be very awkward. I'm just going to take a slightly simpler function. So I won't have 2 here. I'll have a 2 here instead. Well, yes, but I wouldn't. It's still going to be awkward. Yeah, just trust me on this one. Maybe not that awkward, but let's keep it simple. So use the function sine 2x minus vt instead. So df dx is going to be 2 multiplied by cos 2x minus vt. Ah, nice. That's very nice. Now d squared f dx squared is the derivative of that. So that's going to be minus 4 sine 2x minus vt. Okay. Now let's look at df. So we can already plug that in. We can plug that in to here. Now we find df of dt. What's df over dt? Is going to be minus v cos 2x minus vt. Very good. And the second derivative, dt squared equal is going to be minus, so there's going to be another minus v, but then cos is minus, so it's minus v squared sine 2x minus vt. All right. How well do you understand? Do you understand this bit, please, on a scale of 0 to 10? This bit, how well do you understand? Okay. 3, 5, 6, 7. I've got 5 10s and 2 people are quiet. So Ruben, Ruben, you said 10. So who hasn't replied? Rohan and Kieran, tell me something. Do you understand or not? Rohan, yes. Okay. Good. And now we just plug it in. We plug this in. So we plug this into here, and we plug this into here, and magic. Minus 4 sine 2x minus vt is equal to 1 over v squared multiplied by minus v squared multiplied by sine 2x minus vt. Cancel, 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 cancel. Right, cancel. We've got a 4 here. So you get -4 equals -1. I'm wondering, what did we do? Where did we go wrong? Oh, of course. Silly me. It's not V, it's omega. 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 And this is going to be omega squared. So you can see that -4 is equal to 1 over v squared multiplied by minus omega squared. And therefore, I can say that -4 is equal to v is omega. Well, v is equal to lambda multiplied by frequency, and frequency is equal to 2 pi. So v is equal to lambda multiplied by 2 pi over omega. 2 pi omega. 2 pi omega. So plug that in. So lambda squared multiplied by 4 pi squared omega squared minus omega squared. Minus omega cancels out, and we get minus cancels. So 4 is equal to 1 divided by 4 pi squared lambda squared. So you can work out that lambda squared is equal to 1 over 16 pi squared. So this allows you to find lambda, but overall you can see that the equation is satisfied. This equation is satisfied if lambda is this. So, but this is just gives us the wavelength of the wave. Frequency is 2 pi times omega, not 2 pi. What's omega divided by? Oh yes, sorry. Omega divided by 2 pi. 2 pi, of course. Sorry, yeah, the mistake was with the v, and that threw me off. So sorry about that. So that's going to be 4 is equal to 1 over v squared. So lambda squared omega squared 4 pi squared. Omega squared, omega cancels. And we have a much nicer 4 cancels. We've got lambda squared equals pi squared. Basically, lambda is equal to pi. Okay. The wavelength is equal to pi. But I mean, this is the task that you're going to do here is going to be easier because well, it doesn't have the 2. It doesn't have the 2, so that will make sense. Okay. So we've proved that this function is a solution. So this function is a solution of this differential equation. Now, assuming v equals 1 meter, so I shouldn't have done that. So what I should have done is I put x minus vt like this. And then I wouldn't have this problem. But anyways, assuming v equals 1 meter per second, sketch the graph of the function for t equals 0, t equals 1, and t equals 2. So let's have a look. So I have this function. I've limited it between 0 and pi. So you can see this is a piecewise function. It's sine sine x squared. It's sine 2x. Sine 2x, like this. And I can limit it from, oh yeah, that's fine. Sine. And here it's 2x plus vt. So you can see a single wave. You can see a single wave, and then there's nothing. Yeah, so I've just made it nothing so that it's easier to see. Okay, now I change this to 2x minus vt. So here it is. 2x minus vt. Now v in this case is 1 and t is 0. So look what happens as time goes on. So this function is given. Look what happens when I increase the time. It should be like this. Look what happens when I change the time. The wave is traveling. As time goes on, the wave is traveling. Okay. So when t is 0, the wave is here. When t is 1, you can see the wave has traveled 1 meter because it's traveling at 1 meter per second because v is 1. When t is 2, it has traveled 2 meters, etc. So this is the meaning of this wave function. Okay. Jasmine, the what is the y? What is the question? Why? F over, oh, omega over 2 pi, yes. So omega is 2 pi f. Omega is 2 pi f. Okay. Explain how the function describes the wave propagating through time and space. Well, that's what we just did. We saw that if v changes for 2, then in 1 second, it will travel 2 meters. If v is 4, in 1 second, it travels 4 meters. So this is the time right here. Well, for time is 0, it doesn't matter. The speed doesn't matter. So this is, I don't know. When I was preparing this material, I was like, oh, I like it very much. I like this thing. The function that you are given is even more interesting. You'll recognize it immediately when you draw this function. You'll recognize it as something you've meant. That's something you've met before. Okay. And here, so we have a function that in time vt, it travels this distance. So it's a horizontal shift. Look, f of x minus vt is just a horizontal shift by vt. And vt is the distance the wave travels in with speed v in time t. So this should make perfect sense. Okay. Harmonic waves. Harmonic waves is a special type of wave. So the wave does not have to be harmonic. So for example, this is not a harmonic wave. A harmonic wave is just a sine wave, a sinusoidal wave. And a function that describes the wave is like this, but we will write it like this. So you will need to make a, you need to know how to go from here to here using the wave number, k. So you'll read more about this. Show by direct substitution. Okay, so this is easy. You can do this. A wave represented by equation this. Find the wave speed and direction of the wave, frequency of the wave. So you'll need to work it out. Superposition of waves. So this is something you've done in school, right? Superposition of waves. And basically that's adding two waves. So this is example 2. So we have two waves. Wave 1, and we have wave 2. They have a phase difference of phi. Well, that means does everyone understand what the phase difference is? Or do I need to explain? Is there anyone here who does not understand what phase difference is? Please let me know. There's nothing to be embarrassed about. Okay. So I assume everyone knows. So we have two waves, and this is the phase difference. So for example, if wave 1 is like this, wave 1, and wave 2 is like this, then we say the phase difference is 0. If we have the waves like this, we say the phase difference is pi over 2. And if we have the waves, I don't know, like this. Oh, sorry, that's not pi over 2, that's pi. What am I saying? And this is pi over 2. So a quarter of a cycle. Okay, so the phase difference is the lag of one wave behind the other. So the principle of superposition says that the total displacement caused by the two waves is equal to the sum of individual displacements. So f of xt plus g of xt is a sine kx minus omega t plus a sine kx minus omega t plus phi. Okay. Sorry, I need a hint. Okay, so you need the trig identity. It's sine x plus sine y. Sine x plus sine y identity. GT. Here it is. No, that's sine x sine y. Yes. Sine x plus sine y. Sine x plus sine y is equal to 2 sine cos 2 sine x plus y over 2 cos x minus y over 2. So we use this identity. So A goes out of the brackets like this. And like this. So it's going to be A multiplied by 2 multiplied by sine kx minus omega t plus kx minus omega t plus phi over 2 multiplied by cosine kx minus omega t plus kx minus kx plus omega t minus phi over 2. So here kx cancels, omega t cancels, and you're left with minus phi over 2. And then you remember that cos minus x is equal to cos x, because cosine is even. So you can get rid of this minus here. So we're left with 2a multiplied. Now here kx plus kx is 2kx minus 2 omega t plus phi. So this is going to be kx minus omega t plus phi over 2 multiplied by cos phi over 2. So what do we have here? This is the superposition of two waves with different phase. They have a phase difference of phi. And you can see that this thing, sine of that. This is the oscillating part. Yes, so this is still a wave. This is a wave of amplitude 2a. Yeah, 2a. But then it's multiplied by cos theta. So 2a multiplied by cos phi over 2 multiplied by sine kx minus omega t plus phi over 2. So this is the amplitude of the wave. This is the amplitude of the new wave. And you can see that this is the same wave, is just lags by phi over 2. So this wave, the total of the two waves is phi over 2, has a phase difference of phi over 2 with the first wave. But let's focus on this. The amplitude is 2a cos phi over 2. So what does that tell us? That tells us amplitude of the new wave, amplitude of the superimposed waves. If, let's say, theta is 0, if the phase difference is 0, it's 2a multiplied by cos 0 over 2, which is 2a. If the phase difference between the two waves is 0, the amplitude is 2a. But you already know this. You know that if you take two waves that are, that's that's wrong. Well, okay. You already know that if you take y equals sine x and y equals sine x, and you add them together, you get y equals sine x plus sine x. You get a wave of double amplitude. When you adding two waves in phase makes a wave of double the amplitude. Now, if the phase difference is pi, half a wave, then 2a multiplied by cos pi over 2, but cos pi over 2 is 0. So two waves which are in antiphase make nothing, make 0, make a wave of amplitude 0. Please tell me, is the superposition of wave, is it starting to make sense in terms of the wave functions, the wave equation? Yes, it's not a coincidence. It is what we've studied. It's assignment 2 of year 12, the trigonometry. Then we have the principle of superposition, then the differential equations. So this is all very, very cool indeed. Now, if you have two waves traveling in opposite directions, that would be a standing wave. So here you had f is equal to sine a sine kx minus omega t. This is the wave traveling to the right. Minus means it's traveling to the right. And if you have a wave traveling in opposite direction, f2 equals a sine kx plus omega t. This is a wave traveling to the left. And when they superimpose, that's a whole other story. Have we done? Do I have this here? Yes, I have. Oh no. Standing waves. Yes, I've done it here. So you can have a look. A very similar thing. I really recommend you doing it on your own as well, just to see how it works. Okay, and then there are a few problems. There are a few problems on interference. So interference is two coherent waves. So what we've done here is interference, which is based on superposition. A microwave receiver, which is designed to track a satellite as it traverses the sky, is placed on the shore of a lake 3 meters above the water. As the satellite appears from underneath the horizon, the receiver registers a signal of varying strength. Find the frequency of the microwave signal from the satellite with two consecutive maxima of intensity, were 3 degrees and 6 degrees above the horizon. So I won't solve this problem for you, but I will draw a diagram. So you have the planet Earth. This is the Earth's surface, slightly curved. And this is the satellite. Satellite moves. And you have a receiver. You have a receiver here, which is 3 meters above the water. 3 meters. Now, the signal from the satellite travels like this, but also travels like this, bounces off the water and into the receiver. Okay, also put water into the receiver. Now, because there are two signals reaching the receiver, and they're taking a different path. There's a path difference between the two receivers. Okay. Path difference. Path difference. And let's call this path difference, I don't know, X is the path difference. Is it X? Oh no, it's actually KX. Well, KX. Do we need KX? Okay, let it be. Let's keep it simple. Path difference. We've used X, so let's use a different path difference L, for example. Now, if the path difference is equal to n lambda, then you have a strong signal. Strong signal. Yeah, because that's constructive interference. Constructive. And then if L over, why L over 2? Why L? Just L. I'm sorry, it's, yeah, brain's not functioning properly. If L is n plus a half times lambda, that's a weak signal. Weak signal. So you just need to figure it out. You need to draw some accurate diagrams and use geometry to work out the wavelength, I believe. Yes, you need to work out the wavelength. Okay. Do you have any questions about problem 4? Like how to do it? Maybe you're super confused, or conceptually, do you understand why there is a series of strong and weak signals? So the question is, do you understand why the signal changes? Okay. Oh, Jasmine is asking, why is it weak signal and not zero signal? That's a very good question. And let's talk about this separately, because you're taught in school, except a few questions, that destructive interference is when you have cancellation of signal. Suppose you have a loudspeaker. Loudspeaker. Speaker. And you have a wall, or just, yeah, a wall. And you are standing here. So first, you have a wave coming from the loudspeaker, and you have a wave coming from the loudspeaker, bouncing off the wall and getting into your ear, getting to you. So you will experience interference of two waves. Okay. The path, so if the path difference, so the loudspeaker is the source, X, S, let's call this SA, SA. So the path difference is XA plus SA minus SX. Okay, this is the path difference taken by the two waves. One wave traveling from the loudspeaker and one wave traveling through from this. Now, if the path difference is let's say lambda over, well, n plus a half, or, well, okay, if the path difference is, let's say, 40 and a half wavelengths, we have destructive interference. Yes, destructive interference. Does this mean that you will hear silence? If the waves interfere destructively, does this mean that you will, because the wave coming from the loudspeaker would be like this, and the wave coming from the wall would be like this. We add them, we should get 0. Can anyone argue against my logic? Adam, very good. The amplitude reduces with distance. The sound coming from the wall will be much quieter than the sound coming from the loudspeaker. Also, there is a hard reflection, so there's a change of phase on the reflection. I won't go into this. The bottom line is this wave is like this. So rather than complete cancellation, you have a reduced amplitude. Okay, Jasmine, does that answer your question? Yes. Yeah. So instead of for complete cancellation, they have to be of equal amplitude. If the amplitude is different, it's just a reduction. So the reflected signal from the lake might be weaker than the signal from directly from the satellite. It does say it is a perfect mirror, but it still travels slightly further, so it would be slightly less. Okay, a very sensitive receiver might be able to pick it up. And also, when you go into the mountains, for example, I've experienced this a lot. The GPS goes very fuzzy sometimes. It just gives you random. Either it cannot pick up your position, or it shows you a wrong position. Now, this is also to do with the reflection, because GPS satellites send you a signal, and if it's reflected off mountains, that might show you in the wrong position. Okay, the lake surface. Okay, so point source of light. So problem 5. A point source of light is moving uniformly parallel to a plane with 2 small openings. So this is a double slit interference. A light sensor is placed at A, registering the light intensity which is periodically changing. So there's a source of light here. Find the speed of the source if the frequency at which the intensity changes is 15 Hertz. The wavelength of light is tongue. So here you need the double slit formula. We will need the double slit formula. But the bottom line is you have waves coming from S to the slit 1, and then going to S, and then you have waves traveling from S to A like this. So, and there is a path difference. There's a path difference. And therefore, as S moves, this path difference changes. And your task is to work out the relationship between the speed and how the path difference changes. So as S moves, path difference changes. Okay. What else? A laser beam with wavelength splits into two beams. So splits into two beams. So we have a laser splitting into two beams. One goes through a film and one goes through another film. And one of the beam passes through a transparent film with thickness 4.3 micrometers with a refractive index 1.4. Refractive index is 1.4. And here the refractive index is 1.6. So they travel at different speeds. They travel at different speeds. So as they come out, as they come out, they will have a different phase. So here the phase difference is 0, and here's the phase difference is not 0. And so your task is to work out the phase difference as they emerge. Okay. As they emerge, because they take different time to travel through the films. There will be a path. There will be a phase difference. Like taking more time from the point of view of light is just like traveling a longer distance. And as a matter of fact, is exactly like taking more time for light means that it is traveling a larger distance. Okay. So light is interesting. When we say light slows down in glass, it simply means it takes a longer path. The speed does not change. It's just the path of the light change. The path length changes. Now, problem 7. Find the thickness of a so that it looks black when illuminated by green light of wavelength 520. Like if you ever saw soap bubbles, you see that they're colorful. They're very colorful, and this is to do with interference of light. So we have a soap bubble. It has some thickness of which you need to find. Thickness. Ruben, does the V in C and V just relative speed to travel the same distance? Yeah, it's like drift velocity. Yeah, like what is the drift velocity of an electron? Well, it's about 1 millimeter per second. Yeah, it's very, very small. It doesn't mean that electrons move at that speed. Electrons, in fact, travel very, very, very quickly, like close to the speed of light, like probably 50–60% of the speed of light. That's the standard speed for an electron. but it's just the electrons bounce around a lot. They move around a lot, but the total overall movement is that. Okay. It's like oh, that's embarrassing. It says that I've done 1,100 steps this day. Very embarrassing. But as a matter of fact, I am about 8 steps from the place where I woke up this morning. So I move. Do I move 8 steps per day, or do I move 1,100 steps per day? Okay. Yeah. So the film, light comes in. So it's green light comes in, and it is reflected from the film into your eyes. And that would be perfectly fine, except some of the light goes into the film. It is refracted into the film and reflected from the second boundary and comes out as well. And these two rays have a path difference because one has traveled further. There's a path difference, and if the thickness is just right, there you would have a complete cancellation. If path difference is lambda over 2, cancellation, and the soap bubble looks black. Interestingly, is it possible to find black soap bubble looks black? Well, it doesn't immediately give you any. Doesn't immediately give you any pictures on this approach, but the fact that they are rainbowy when you look at soap bubbles, they're colorful. The fact that they're colorful tells you that there is interference there, interference of different wavelengths, and so the colors that you see are the colors that are constructively interfere. Okay, so when you see a soap bubble, which is quite cool. It's illuminated by white light, but only certain colors get constructively interfere. So we've done standing waves. Yeah, so you can figure that out. The Michelson experiment. The Michelson experiment is an experiment to find the speed of light. That was a brilliant experiment. So what happens here is light comes in from the source, and then it bounces to the mirror. The mirror is quite far away. It's 35 kilometers away. Yes, the mirror. This is 35 kilometers. 35.5 kilometers. And then it bounces. Well, it bounces of another mirror here. You can ignore this bit. This bit is very, very short. And then it bounces back. Now, by the time it moves, this reflecting bob has to turn 45 degrees. So if it by the time the light reaches D, it's in exactly the same position as it was before, that means you will have a reflection into a view piece, into T. If it turned not exactly 45 degrees, then it will bounce off into a different direction because this will not be in the same position. And what you need to measure is you need to measure that speed. You need to calculate the frequency in order to have this. So this was the first one, not the first. It was the most accurate measurement of the speed of light to that date. Yes, so Michelson experiment. There's also the Michelson-Morley experiment. They were trying to determine if there was an ether or not. They were trying to measure the speed of light in different directions. And if the speed of light in different directions, different perpendicular directions was different, that means the planet Earth is going through a substance called the ether, which they thought was true. But they found no difference. They saw that the speed of light is independent of the direction in which you shine the light. The Huygens principle, what I think I wanted to discuss with you, yes, the Huygens constructions. So how it works. So let's say you have a wave. So a wave is traveling. Now Huygens thought that every single point on the wave is a source of secondary waves. So if we draw that, because there's infinitely many of those, they all add up to a single wave, which is the envelope. So this is the envelope of the wave. So this is the addition of all these infinity waves. And this is how the second wavefront appears. And now the second wavefront is also, every point is a source of secondary wavelets. And this is how a wave propagates through space. That's what he thought. That's what Huygens thought. And even though it turned out to be completely wrong, the principle allows you to solve problems on waves, on wave optics in particular, very, very accurately. So we still use the Huygens principle, even though it is, false in many ways, because every point on the wave is not a source of secondary wavelets, but the mathematics works. Does the Huygens principle make sense, what I've shown so far? On a scale of 0 to 10, please. Okay. So the Huygens principle, just recap. So if you have a wave, every point on that wave becomes a source of secondary wavelets. So let's say we have a wave coming in. So the wave is traveling that way. It's a circular wave. So we can say that every point is a source of secondary waves. And if you add all of these waves, small waves together, you will get another wavefront. So Rohan, Ruben, does that make more sense? Okay. And this allows you to, this explains diffraction. Because if you look at diffraction, Hello. Oh, why it's useful if it's incorrect. The Huygens principle allows you to predict very accurately the behavior of waves, but for the wrong reasons. Okay, it's like when I worked in a school. Well, I worked in a school not that long ago, until September. I could very well predict that if I have a maths test, and I ask this, and this is the height of a student, and this is the test score. I could very accurately predict that taller students will do better. There will be a very, very strong correlation between the height of a student and the test score. Why is that? Because they are older. Very well. They are older. The taller students tend to be older. So if a student is 180 centimeters, they're probably like 15 or 16 or 17 years old. They will do better in the same test than a year 7 student. Now, does my model predict the test score based on height of a student? It does. Is it a correct model? No. Okay. I can make predictions for the wrong reasons. So I'll delete this out of context piece of information. So my model makes accurate predictions based on wrong assumptions, but it works. And the same is something similar happens with Huygens principle. Okay. There's a question. By constructing wavelengths, show that the law of reflection can be explained by Huygens principle. Oh, we were talking about the ripple tank. Sorry. So let's talk about diffraction. Single slit. I have a single slit, and there are waves coming in onto a single slit. And as they pass through the single slit, they spread out. As you can see, they're spreading out of waves. And Huygens principle allows to explain this very, very well and very easy to understand. So if you have a slit and there are waves coming in, onto the slit. Every point on the slit becomes the source of secondary waves. In other words, we have waves spreading out like this. And actually, the narrower the slit, the wider they will be spread out. So for a very narrow slit is just like this. Okay. So every point becomes a source of waves. These kind of add up like this, and you have waves spreading out. So this is diffraction. Diffraction. Double slit interference can also be explained using Huygens principle. You have two slits and you have waves coming through. So you have waves incident on the two slits, and you have two waves. Okay. Now, the law of reflection. So how does it work? Well, you need to say that the mirror becomes a source of secondary wavelets. So as waves fall onto the mirror, they reflect, and you can see that all the reflections will add up. So how does that work? I'll show you for a diffraction grating. So diffraction grating is basically a diffraction grating. Yes, should I remind you guys what the diffraction grating does, or are you fairly familiar? Diffraction grating. Grating pattern. Pretty much. Diffraction grating pattern. This kind of pattern. Yes, with monochromatic light, it looks like this. With white light, it looks like this, but we're focusing on this. So if you have a diffraction grating, and a beam of light hits the diffraction grating, and you will have several directions. So at the other end, you will see dots or fringes. This is the central maximum, central max. This is n equals 1, n equals 2, so n equals 0, n equals 1, n equals, well, minus 1, n minus 2. Okay. And this is the diffraction grating. Now, these are the directions at which you have maximum. So you have just to make sense of it. So this is the central maximum, n equals 0, n equals 1, n equals 2, n equals minus 1, n equals -2, etc. Okay. This can be, and I really love it. So let's say we have a diffraction grating and the slit separation is d. So this is the d is the distance between slits. Okay. So a wave is coming in. So a wave is coming in. And of course, as the wave comes through, it will diffract. And every point, every slit in the diffraction grating becomes the source of secondary waves. So this becomes a source of secondary waves. This one becomes a source of secondary waves. This one becomes, and this one becomes. And as you can see, they all add up in a wave that is traveling in this direction. And that's the central maximum. That makes perfect sense. That's the central maximum. But let's draw some more wavelets. They use a different color. Let's see. Okay. And now, if you look at it very carefully, you will see that this is not the only wavefront that appears. Also, we have a wavefront made up of this. Difficult to see, I know. But if you see that this wavefront, it touches this one and it touches this one, and it's producing a wavefront that is traveling in this direction, and that is the n equals 1 direction. Just do it here. So you can delete that. All right. So D is the distance between the slits. So D, that's D, the distance between two slits. And you can see that there are wavefronts. So wavefront, yes, which just touches 1, 2, 3, 4. The second wavefront, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, and that gives you the central maximum. That's the direction of the central maximum. So they are all traveling in this way, and that means this is the n equals 0. Okay. But then, just like magic, we have another direction. If we take this wave and the first wave, if we take this wave and the third, second, and first, third, second, fourth, third, second, first, fifth, fourth, third, second, first. You can see that these waves add up. Now, I really encourage you to practice drawing this. And here we are. Here we are. And here we are. And here we are. You can see that these waves are all traveling in this direction, which is direction to the first maximum. N equals 1. Does this make sense? Please tell me. On a scale of 0 to 10, do you see it? Do you see how I made that? Very good, Ruben. Nice. And from here, you can work out the equation, because look, if we take this slit and, for example, this triangle, this triangle, okay, this angle is theta. This is 3 lambda, because the distance is 3 wavelengths. 1, 2, 3 wavelengths. This distance is d, and this distance, well, let it be x. We don't know x. Okay. And 3 lambda. And here, we draw here, this is 2 lambda. This is 2 lambda. Now, sine theta is equal to 2 lambda divided by x, but also sine theta is equal to 3 lambda divided by x plus d. I'm using this triangle. Yes, so the sine of this angle is 3 theta divided by d plus x. And also sine theta is equal to 2 lambda divided by x. So I equate them. 2 lambda over x equals 3 lambda over x plus d. And then lambda cancels. I get 2x plus 2d equals 3x. X equals 2d. Incidentally, which is fine. So sine theta is equal to 2 lambda divided by 2d, which is lambda over d. So d sine theta is equal lambda, which is the formula. It's just missing the n, but n is 1. This is for n equals 1. So we can prove this formula just using these constructions. So Huygens principle, incredibly useful. And one last thing is the polarization. Is Malus's law, and I think we'll talk about it next session. So next Thursday is going to be the last one of this year. Next Thursday. Yes, next Thursday we will have at the last session. I'll probably talk about waves. And then we have 2 weeks break. And then we are back in January. Okay. Well, thank you for your attention today. All right. Hope you've learned lots of new stuff. And see you.
I didn't really get about the constructions, not the parallel ones, but the other ones. How did you do them?
Which are you talking about? This one?
Yeah, like I know how you did the parallel ones. You just connected all the all the parallel lines, all the maxima together to create the wavefront, but I don't really get how you did the other ones.
So you mean you know how I did the central one, but you're not sure how I did the first maximum. Is that what you're telling me? Yes.
Yeah.
Okay. So if you take, so to get the first maximum, the central maximum, you take the first wave, first wave, first wave, first wave, first wave, and you combine them to make a wavefront. Yeah, that's fairly obvious.
Yeah, because you're just you're taking all the maxima.
Yes, all the maximum. Well, they're not. It's not the maxima. It's just the wave. The wavefronts. The wavefront is the part of the wave that is moving in phase. So the black line is the wavefront.
Yeah, so it might as well be a maxima just for convenience.
I wouldn't call it the max. Oh, okay. Yes, it is the maximum. So now if I take the 1, 2, 3, 4th wave from here, I take the 3rd wave from here. I take the 3rd wave from here. So 4, 3. I take the 1, 2, 3, 4. Sorry, that's the 5th wave, the 4th wave, the 3rd 1, 2, 3, the 3rd wave from here, the 2nd wave from here, and the 1st wave from here. 1, 2, 3, 4. And I combine those 5, I get a wavefront in a different direction. Do you see that?
Oh, I see. But then surely you could do that like to create infinitely many n's, like n equals 10,000. But we know that if we do that with a diffraction grating, I remember doing this at school, I only get like 10 or 12, or say if I'm really lucky, I don't get infinite.
Yes, because look, at some point, this is not infinite. Because to get the second maxima, you need to take this. You need to take 6, 4, 2, 0. Yeah. You need to take the 6th, the 4th, the 2nd. So you go in 2s, right?
Okay.
Now, if you want to go the 3rd maxima, you go 6, 3, 0, etc. Now, if you want the 6th or 7th maximum, look, you need to take the 1, 2, 3, 4, 5, 6, 7. Let's say you want you want n equals 7. So you take the 7th wave from here and the 1st wave from here. These two waves do not have a common tangent, so it doesn't work. So it will work for n equals 6, but not for n equals 7. See, so for n equals 6, it will work because these two lines have a common tangent. These two waves have a common tangent.
Okay. Can you quickly remind me how do you know which wavefront to pick? So for the 6th or for the 5th, it doesn't really matter. How do you know which one to pick for the top one?
So if you take the 1st and 1st, that's n equals 0.
Mm-hmm.
If you take the 2nd and 1st, that's n equals 1. If you take the 3rd and 1st, that's n equals 2. If you take the 4th and 1st, that's n equals 3. So if you want to take the 7th and first, that will be n equals 6. Sorry, I said n equals 7, n equals 6. I mean, I made a mistake here, but the idea is that you take the 7th here and the first here, and that gives you n equals 6. So 1, 2, 3, 4, 5, 6, 7. So this is the 7th wavefront, counting from the center, yeah? And you take the first wavefront here, and you see that they do not intersect. They don't have a common, they don't have a tangent. They don't have a common tangent because one is inside the other. There's no way you can draw a tangent that touches both. Make sense?
I think so. Yeah. Thanks. Yeah, I get that now.
Yeah, that's why you're limited with the number of maximum.
And then you know that they won't. You get the situation that you've drawn on the right here when now depend on the wavelength and like the order, and you can use that formula to help you think about when sine of theta doesn't really exist.
Exactly. Yeah, when theta is 90 degrees, that's your limit.
Oh, okay. Yeah, fine. I see.
Yeah.
Okay, yeah.
All right. Okay.
Cheers. Thank you.
See you.